Okay, let's get started. So today we're going to talk about the CPM, about something about project schedule and CPM. CPM is critical path method. So we will use the tool called critical path to help us with the management, the scheduling of your project. We will see how can we calculate the critical path of this project. Okay, so we will see an example and we will do some exercises today. All right. Okay, and we have this all this material. Actually, all of you are enrolled in this face-to-face in hybrid session. All of you are enrolled in exactly the same session in the D2L. You have exactly the same access with the online student to all the course material there. Okay, so since this is a hybrid session, what I mentioned here in the lecture in the classroom is whatever I think is critical in the course and whatever is important. And that doesn't mean all those materials I didn't touch, it's not important. It doesn't mean that. Okay, they are also important. You need to follow the instructions of every folder and do what the online student do as well. Okay, to go through all these materials. Okay, and what I mentioned here, it's gonna be something critical, the really critical skills I want you to have to learn from this course. Okay, so remember to follow the instruction to go through every materials in each folder. All right, got it? Okay, like this week we actually have two different sections. One is the scheduling, another one is the requirements, basically. So but in this lecture I'm gonna only cover the scheduling, the CPM thing, but the requirements is something that you need to go through when you are at home or sometime after the class, and also you will find some of the information useful when you're doing the project. But the thing I mentioned today, I introduced today, is probably going to be in the exam. Okay, so yeah, try to not just only follow my lecture, also follow all the instructions and the materials. All right. Okay, so today we're going to talk about this project scheduling with a tool called CPM. Okay. Okay, when we're trying to schedule a project, we have some tools that can help with us. So, but why do we need to do the project schedule? First, we want to control our the cost on this project, right? So we desire we use the project schedule to describe the software development cycle, and we try to break down the whole development process into different phases. And also in each phases we need to break those into different activities. Okay, and then we know that how different activities they interact with each other. By saying interaction of the activities, I mean for some of the activities you cannot start it before its predecessor finished, right? Like you can't listen to my lecture before you entering this classroom, right? You have to go to school from your home, right? Drive to school. Well, this task has to be finished before you actually sitting in this classroom, something like that. Okay, so it has a dependency. We have some tasks depends on the other, but some of the tasks are irrelevant. For example, if you are doing a building, okay, well, maybe you have two different activities. You paint the wall inside and you paint the wall outside. Those two tasks, they are not really depend on each other. They can happen same time simultaneously, or but just maybe some overlap or not overlap at all. But it just depends how it is scheduled, how you plan for that. But it's just flexible. One thing doesn't have to be happen after the other. Okay, but just those two activities, paint the inside wall and paint the outside wall, probably they will have some common predecessors, right? So like some activity needs to be finished before we paint. So what can be that? Yeah, you have to have a wall first before you paint the wall, right? No matter it's outside or inside, right? So they should have some common dependencies on. First, build the wall, something like that, right? Okay. So this is how we do the project. Okay, the whole project we can break them down into phases, and then we can have different steps of the phases. In each steps, we can have actually the activities. So the activity is actually the most elementary thing there, the basic element there to build up this whole project. So here, when we are talking about critical paths, we actually working on our scheduling according to the activities. Later on, you will see the example. Okay, this is just to give you a brief introduction overview. Well, this is actually the activity graph of building a house. We can take a look at this. Let's see, we have like the starting point, which is the solid gray point there, the circle there, and we have a 0.1 activity, 1.1, 1.2, 1.3, 4, 2.1. You can see that for example, the 1.4 by materials and 2.1 lay foundations. They have the relation that one has to happen after the another, right? And one cannot happen before the finish of the previous activity, right? Okay, but here, when we reach 2.2, at this point, 2.2, we actually have two branches, or those 2.3 and 3.1, which is built out installing interior plumbing and install exterior plumbing. They don't really have some dependencies on each other, right? It's easy to understand. And later on, you have two branches. Then at some point, they merge to the finish line. Yeah. So it's just a activity graph. Actually describes that, well, some of the relations between among this activities. Okay, so give you a visualization of these activities, these relations, more importantly. Okay, so this graph is easy to understand, right? Any questions? You can read this graph, right? We have a start point, we have a finish point, and we have different activities. Right? Yeah.
So how do they go from 2.7 to the finish and then 2.8?
Right.
The paint exterior.
2.7. Yeah. You don't go from 2.7 to 2.8. You go from 2.7 to finish. You also go from 2.8 to finish. Right. So installing roofing. 2.7 is install exterior doors and fixtures. that really doesn't depend on each other. Yeah.
So 2.3 and 3.1 can happen at the same time?
2.3 and 3.1. Yes, it can happen at the same time or not. It just doesn't matter, yeah. Okay, so there are a whole bunch of branches which you can paths which you can go from start to finish, right? Go from this way, go from right this way, right? Okay, so there will be the length of this whole project, like the duration of this whole project. Well, it's for example, if we go from like 1.1, 0.3, 0.4 to like this way, 1.1, 0.3, 0.4, 2.1, 2.2, we go all the way to 3.1, 3.2, 3.3, 3.4 to finish. Another way is we go from here to the left side to 2.3, 2.4, and 2.7, go to finish. Okay, let's assume, let's assume that if we go to the left, like install exterior plumbing, it will take us 6 months. And when we go to the right side, this pass will take 7 months. Alright. And what do you think the whole project will take?
A year. Is it 2.7, 7 months and 6 months?
Yeah. So if we like here, we from start to finish. We probably have 1, 2, 3, 4, 5. We actually have four different branches to here. But now I'm telling you, one of the branch like this, it takes 6 months. One of the branch here, this way, it will take 7 months. Maybe another branch here take 5 months. So we have 4 branches. Which of them take 4 months, 5 months, 6 months, 4 months, 5 months, 6 months, and 7 months. Okay. So what do you think will be the length of the whole project?
7 to 8 months.
7 to 8 months?
It depends, like, because if you can do some at the same time, then that'll just take that amount of time. But then if you have to wait for one branch to finish,
Yeah.
start the next branch.
Yes. Yeah, it depends. Let's see, what do you think would be the shortest amount of time to finish the whole project?
So you said 4
Shortest
branches.
possible. 4, 5, 6, 7.
7 months. The whole project? Or
Yeah, the whole project.
7 months.
Yes, it's a 7 months. Well, the shortest amount of time really it depends on the longest pass, right? Longest pass. So it's not the sum of all of them, because some of them will happen simultaneously, right? It's not the sum of them, it's the longest one. It depends on the longest one, right? Okay, so with that in mind, we know the longest pass is actually called the critical path of the project. Okay, remember, critical path is the longest path. It's the path that takes the longest time to finish. Like here, we actually mark the time beside this line. The time is 3, 10, 10. Just for you information, within the circle it's the number of the activity. Maybe 1.1, activity 1.1, activity 1.3, 1.4. But along with these lines connecting all those activities, these lines actually tells you some of the information, which activity happens after which. And along the lines we have the time of the duration of the activity, like 2.8, activity 2.8, it take actually time is 9, right? And the finish, this finish activity take time 0. Why is that? Because that's just a finish. That's basically it's a dummy node. It's a dummy node. The start and the finish, they are dummy node. Everything connects to the finish, That just let you know that this is a finish point. It really, this activity doesn't take any time, so that's 0, right? Then how about 3.1? How do you think, how long would 3 point would be the activity 3.1?
15.
It's actually 12.
Oh, really?
Yeah, you go from the start.
Like you meant like to get
Yeah.
3.1 or to get to 3.2?
3.1.
To get 3.1?
Yeah.
It's 12.
Yeah. The duration of 3.1 is 12. Okay. So you kind of find the path from the start to the finish. You find the direction. You find direction, then you know that, well, you have to go through. This 3.1 really means the finish of 3.1.
Oh.
Okay. Okay, then it's critical path. Critical path method. That's what we will do today from this material. So why do we need this critical path? First, like I mentioned, we need to schedule. We need to schedule our activities for the project. All right. So we need to monitor our progress of the project. We need to monitor the cost, and we assign the resources to a project. All of this, we basically we need a correct scheduling tool to help us. So critical path method is one of this, and an important one. Okay, so in order to understand what is a critical path, first let's look at the right upper side, this table. So this is a table which describes the activities, the durations, and the predecessors. Okay, what is activity? Activity is maybe a subtask or a subdivision of the project, okay, whose execution requires time and resource. Right. So like for this whole project, we have activity A, which is a start. Start means it's a dummy node. It doesn't really take time. Okay, but it's start. Okay, so and we have so duration is 0, and those H finish duration is 0. Those are two special activities. Take 0 time. They are basically dummy node. Okay, and also we have activity B through G, which has a duration of 7, like 3 of them. It can be days or it can be hours. It's just a relative. Okay, relative. Also, in this table we describe predecessors. What is predecessors? I just mentioned a little bit. So with which let's see. For example, the activity B has the duration of 7 days. That means we need 7 days to finish this task. Now we have 7 days. It's like we need to spend 7 days to finish activity B. And then the B has predecessors of which is an A, means you cannot start doing B until you finish A, right? And here another example, we have activity E, which take 9 days to finish, and E has predecessors of B and C, which means both B and C has to be finished at the point you start E. Okay, that's called predecessors. So here B and C is called predecessors of E, and E is a successor of B, and E is also a successor of C. Okay. All right. And here is another matrix to help to express this relations between successor and predecessors. Okay, so here we have A as a predecessor, so we need B and C. We need A we need A to be finished in order to do B and C. Okay, we need B to be finished in order to do D and E. So this matrix is give you a more clear view of the relationship between all those activities. All right, and another expression is here. The activity on node network. Right, so we have this activity as each node, and then when you have a successor, you connect from this activity to the next activity, and it shows that B has the predecessor of like as A, and like E has two predecessors, which is B and C. So all of them, they kind of tell you the relations between all those activities. But this activity on node network, do you think this is more clear? Right? Which one do you think? If you want to tell the relations, which one do you prefer?
The second one.
The second one? Any reason? Any reason why you prefer second one?
It's kind of simple.
Yes.
The last one is kind of tricky.
Okay. Well, the second one, actually, if you want to check whether any individual activity has a predecessor or successor, maybe it's more clear. But if you think from the perspective of the whole project,
For the whole project?
right, that's going to be the last one. Okay. So when we're doing the CPM model, the critical path method, we well, what do you think? This is the first. This is the first view. This is the second view. This is the third view. I mean, just to tell the relations between each activities, which one do you think is more clear? Well, it should be the third one, right?
So at some point,
Second one? Second one, well, it's kind of similar to the first one. If you want to check, well, any individual. Well, no. Actually, for the first one, if you want to check the predecessors of D, it's easy to check. Yeah, we have a B as a predecessors. But if I want to check what is the successors of D, you have to check this table, right? The successor of D is, well, the F, right? Well, the predecessors of D is B, yes, and the successors of B is F. So here, well, you have to kind of check it, but here I can just tell you the D. Okay, the successor is F. The predecessor is B, right?
so they all become successor in the other one, like at some point, right?
What's your question? Sorry.
Like E is like, for example,
E. Okay.
it's a successor for F, right?
No. E is actually, well, F is the successor of E, and B and C is the predecessor of E. What happened before is called predecessor. What happened after is called successor.
Oh,
Okay.
got it.
So here, what happened before E is you have to have B and C, right? So B and C is the predecessor of E, and F is the successor of E. Yes. And C here we have two successor, which is E and G, and it has one predecessor is A. Okay. But one of the information here is missing, like the durations is missing from the graph. Actually, there's an easy fix. You can just put the number on the edge, right? So the CPM will based on this activity on node network. Okay. Yeah. Let's before we talk about the CPM, I need to introduce this for theories or definitions. So it's ES, EF, LS, LF. So it's earliest start, earliest finish, latest start, latest finish. Earliest start time, well, this actually is the cell for each activity, like here. C. When we're doing a critical path, we first separate this activity into these 4 parts: ES, EF, LS, LF. So it's the earliest start time, earliest finish time. That means the earliest time you can start this project. And then the earliest finish time is the earliest start time plus the duration of this activity, right? Like I can start a lecture at 5, and I have an hour duration for the lecture. So earliest start time, earliest finish time is gonna be 5 plus 1 hour. It's gonna be 6, right? And I have to finish this course. I have to finish this course, this class, this lecture at 6:15. That means the latest finish time. So what's gonna be the latest start time of this lecture? I mean this. 5:15. Yes. So latest finish time minus the duration of this activity is gonna be latest start time of this activity. And the other way, latest start time plus the duration is gonna be latest finish time, right? Okay. So we replace each of the node with by a square which has been quartered. So we have 4 sections here. All right. Then we need to follow this step. Step 1 through step 8. Let me quickly go through. Maybe you'll get confused, but let's do this. Let's do this here. So when we are creating this CPM for this activity, for this A, B, C, D, E, F, G, H, okay, the first step is we place the project start time on or date in the earliest start and the earliest finish positions of the start activity. The start time is 0 for relative calculations. So this is going to be the first step. Reversed, right? So let me see, how can I do this?
There's a rotate button right here.
Where?
Right click it. Rotate that
Oh, nice. Didn't see that. Okay, this is nice. So you're gonna have this here. Let me put this. I need to pour this out in order to give you a reference. we need to have this. I will put this on. Okay, it's fine. So you remember the ES, EF on the top, the LS and LF on the bottom, okay, of each cell. So the first step says we need to put the 0 at the starting point, okay? So since it's A is start, the duration of A is 0, right? So here the early start time of A is 0, right? Yeah. Hey. Well, I think I need to do another here. Put this here for reference. Okay, this looks much better. Is it clear? Yeah.
Can you make it right bigger? Maybe you can like make it bigger on the PDF and then just screenshot it.
Yeah. That's crazy.
Yeah, right.
Yeah, let's do this. I just need this section. This is better. Okay. Now the first step we need to put here the earliest start time of A. A is actually the dummy node of start. So it's going to be 0. We start everything at time 0, right? So earliest start time is A. 0. Right? And how about the earliest finish time of A? 6? Why do you think that's 6?
Because C is a C is the successor.
Yeah, 6 successor.
So if it finishes in 6, then C can start.
I mean, this is a starting point, right? In order to start, you really take the duration is 0, right? So the earliest finish time equals to the earliest start time plus the duration. So earliest start time is 0, duration is 0, so earliest finish time is 0. Right, so that's a special node for the start, okay? It's not B, right? It's not that.
You said early finish is early start plus duration.
Yeah, yes. Earliest finish is the earliest start plus the duration.
So
Yes.
0,
0, 0. Okay. And then let's go back here. Let's see what is the second step. Okay. Second step. Consider any unmarked activity, all of whose predecessors have been marked in the EF and the ES. And mark it in the ES position the largest number marked in the EF position of those predecessors. That sounds a little bit crazy, right? But let's do it. So first, it asks you to identify all the cells that is doable now. Excuse me. Well, here, can we do D at this moment? No, because D needs B. But we can do B at this moment, right? Because B needs A, and A is finished, so we can do the B. And the earliest start time of B. Yeah, it's the smallest earliest finish time in its predecessors. I'm sorry, largest number. Largest number, yeah. But since it's only have one, B only have one predecessor, so it's gonna be 0 here. And B's duration is 7, so what is the EF of B?
7.
Yes, correct, 7. And how about C? What is the ES of C? 0, yes. Yeah, and 6. Yeah, so far so good. Now can we do D? Yes, since D only have one predecessors, right? So yes, it's gonna be 7. It's the largest number of the EF from its predecessors. Okay, this one is tricky. How about E? What is the ES of E? Earliest start time. Remember, it's largest. It's 7, right? Because you see, we have a C. At moment 6 we finish C. At moment B, at moment 7 we finish B, right? So only when B and C they are all finished, then we can start E. If it's at moment 6, only C has finished. We still need time to finish B before we start the E. So here the ES of E is actually dependent on the largest number from B and C. Okay, so it's gonna be 7. Clear this part? Yeah.
Why now 8?
8?
I mean for D and E, why now the EIs is now 8? Because after 0 to 7, the next moment is 8.
Oh, you mean the next moment. Actually, at the moment you finish B, you should be able to start D. You don't have to wait for another day. Right? Why do you wait for another day? I mean the earliest day. The earliest means the earliest possible. Right? I mean after this class you can go home. The earliest time you can go home is 6:15. Right? The earliest time I can maybe I finish this course maybe 6:15. But also yes, you can go home at 7:15. That's fine, but that's not the earliest. So earliest is gonna be 7, right? Okay, then this part is easy. The EF of D is going to be 7 plus 10, yes. And how about this? Correct, 16. Okay. Now we have another set here, F. So what is the ES of F? F is enabled, so here is 16, correct. It depends on the largest number from its predecessor. So it's 16. And how about G?
It's going to be 6.
Yeah, it's 6 because it only has one predecessor. And the finish time is straightforward, 16 plus 1, right? It's 17. And it's 6 plus 4, it's 10. Okay, then we got the earliest time ES of the finish. It's gonna be, yes, correct, 17. And since this is actually also 17 because that's dummy node, all the starting and the end point they are all dummy nodes, so the ES and EF they are the same. Okay. All right, so that's for the ES and EF. We get it from the start. We fill in the ES and the EF, and then we doing through several iteration. We try to check which activities has been enabled. Then we put the largest number of its predecessor's EF into its ES. All right. Yeah, I feel this way it will give you a clear view of how to do this. So then for the next step, we still need to figure out the LS and the LF, latest time. Okay, so let's finish this step 4 and 5. Step 2 and 3 is for the ES and EF. 4 and 5, let's see. So place the value of the latest finish date in the LS and LF boxes on the finished node. Okay, here, what is the latest time of finish to finish? What is the latest time to finish the task?
17.
Yeah, it's also 17 because we didn't have more information. Just it's going to be equal to the earliest finish time, so it's going to be 17 at this example. Right, okay, 17. It's also going to be 17 because LS is the latest time to start. Okay, since it's dummy nodes, it's going to be all the same actually. Yeah, so it's 17 because it's because it's 0, right? So H takes 0 time to finish. So the start and finish, they are the same. Okay, and let's see. Place the latest finish time and date, start time. Then step 5, consider unmarked predecessors whose successors have all been marked. Their LF is the smallest LS of the successors. So we go backward. This time we go backward. Okay. We find all the predecessors of H, which are, yes, exactly, F and G. And then for F and G, the latest finish time is the smallest latest start time of the successors. So LF, we put, what number do we put here?
17.
Yes, exactly, 17. Right? Okay. And how about this? The latest start time. It's gonna be the latest finish time minus, yeah, minus 1. So it's gonna be 16.
Why is it? Oh, because
Yes. And how about this one? Latest start time. 13. Yes. Because it's 17 minus 4. It's gonna be 13. Okay. Right now we have some other cells that's enabled. Okay. For example, oh, this one is not enabled because it requires actually F. It has F as its successor. So here we actually have F. Predecessor of F is D and E. Now let's see here. We just put 16 because it's only had one successor. It's gonna be 16. And it's gonna be 16 minus 3, 13. Here, this is also 16. Gonna be 16 minus
Take the highest
7.
or L1?
What's it?
Take the highest, 16?
This 16. This thing actually it would take the smallest. When you go backward, take the smallest. When you go forward, take the largest. Okay. So this is a tricky one. Which one is that? 7 or 13? 7. Yes. That's the latest finish time of C. Because if you think if you make C finish later than 8, then E won't be able to start at the time of 7. Okay, so that violated the latest start time of E, which is 7.
Latest finish time always has to be larger than earliest finish time, right?
No. Well, it's gonna be larger or equal to. It can be equal or larger. It won't be smaller.
Oh, yes.
Yeah. Yes. So this is 7, and C takes the duration of C is 6. So it's gonna be 1 here. And for this one, it's gonna be 7. And since it takes 7, so it's gonna be 0. Yeah. Well, okay.
So basically, the first, like the start and the finish are always going to be the same number.
Start and finish.
Because A is 0, 0, H is 17.
Yeah. Well, okay, it's gonna be the same. Start and finish is gonna be ES, EF is gonna be the same. LS and LF is gonna be the same. But it's not necessarily that here. We may have a different finish time, latest finish time. Yeah. If you think you can introduce some maybe select time or something like that there. It's possible. Yeah. Okay. But in this case, they are all the same. Okay. Okay, so here it's gonna be we finish the sale of this thing. Now let's see how can we identify the critical path of this project. Okay, so let's go back here. First, we need to calculate the slack time for each node. It's gonna be LS minus ES or LF minus EF. Actually, they are the same. Understand? Latest time to start minus earliest time to start. It actually equals to latest time finished minus early time to finish. Right? Logically, it's the same. So let's calculate the slack time for each node. All right. So it's gonna be, let's just use LS minus ES. Okay. So LS minus B is the slack time of B. LS minus ES. It's going to be 0, right? Because you cannot have slack time here. You just finish it. but slack time of C is gonna be 1. Well, does it make sense to you? Why the slack time of C? What do we mean by saying the slack time of C is 1?
1 minus 1.
Yes, 1 minus 0 or 7 minus 6, right? Well, and slack time is 1 is because that B and C actually when you finish C at this moment, at moment 6, you actually have some that slack time. You don't have to push yourself into the task E because we are still waiting for the B to finish, right? It takes 6 days to finish C, but it takes 7 days to finish B, right? Like if we are in a group, we are working on some project. Okay, I took 2 days to finish my project, while you take 4 days to finish your part. After we all finish, we can do something else. So after I finish at the day 2, I have 2 days. I can be slacker. I can do nothing to just wait for another task to finish, right? Okay, so the slack time of C is going to be 1. Okay, let's calculate. For the D, it's going to be 6, right? 6. And for E, it's going to be 0. And here it's going to be 0. This is going to be 0. Oh, no, it's going to be 7 slack time, right? Okay, so we have the slack time for each of the activities. You can see, actually, in G, we actually have a whole bunch of a large slack time there. Right. Okay, so how can we identify the critical path? It's going to be the critical path encompasses nodes for which the slack equals to the LS minus ES. LS from the start node. LS minus ES. Latest start time here. Okay, latest start time and minus ES, right? LS minus ES. Latest start time minus the early start time. It's 0, right?
We don't just like add it together.
No. Here. Now our task now is to find out those nodes that is in the critical path of this project. Okay. So how can we identify the nodes? Now we have all this slack time of the nodes, right? But now let's calculate the LS minus ES of the start nodes, which is 0. So we just found the 0 here, okay? And then for the critical path, it includes all the nodes for which the slack time equals to LS minus ES. So the slack time equals to 0. For those nodes whose slack time equals to 0, those nodes are included in the critical path of this project. Let's see. So the 0 we have this B node, right? Is 0, and E is 0, and F is 0. Yes. Yeah. So for those nodes whose slack time is 0, they are actually in the critical path. But how is the 0 calculated? It's actually this LS minus ES of the starting point. Okay. So it's 0. So the critical path is Can you tell me which is critical path of this activity?
A, B, E, I, H.
Yeah, it's gonna be from A to B, then you go to E, you go to F, you go to H. This is a critical path, and this is the longest path. Okay, because on this path, all the activities they actually have no slack time at all. So and it's what we have to do this one after another, one after another. After finish this task, we will do something else. After finish B, we will do E and D. After finish E, we will do F, without any slack time. But here, other nodes, they are not on critical paths. Okay. Well, this is how we identify the critical paths of the project. Okay. However, here actually, one project may have more than one critical path. Okay, let's assume that if we have this activity C select time as 0, so we will have another road from A to C to E, F, and H. It's possible. Okay, we may have more than one critical path. All right, so it's possible, but the critical path is the longest path. Remember that. All right. So, okay. Any questions? It's easy, right? You just need to follow those steps. First, put something in the start node. We go forward. We find the enabled nodes. We go forward all the way to the end. Then start from the end point. Go all the way back. Then we calculate the slack time and select those slack time that equals to the ls minus es of the start. Then we can find out the critical path, and that's also the longest path. All right. Okay. So that's the main thing I want to talk about today. And we have another exercise here with this figure. It's actually
This is supposed to be next week, right?
yeah, it's yes.
It's Monday?
Yes, I think I put it on Tuesday or Monday next week. But let me go through. It's actually you need to find out a table on the textbook. So I'm trying to find it. Downloading? Why you're downloading? Oh, it's not in my computer? That's weird. That's okay. But this thing, it's gonna be, yeah, this is gonna be more complex critical path calculation, because it has like 20 nodes there, something like that. So please try to do it, and the table is on the textbook. I think on page 98, somewhere around that. Okay. All right. So any questions regarding this critical path? Yeah, it's so easy to understand. That's great. You guys really understand that's really fast.
So if you're gonna go backward, you always do EF and LF, right? And forward is ES and LS.
Yeah. So here, let's look at the cell. When you go forward, you kind of you're doing this earliest. When you're trying to decide early, you go forward, right? So here, the ES it depends on the EF from its predecessor, largest EF of its predecessors. When you go backward, like here, like this cell. Okay, example. So this cell, it depends on the cell here. It also depends on this cell here. Right. These two cells. And when you go backward, actually, we're trying to fill in this cell. This LF. It depends on the smallest LS of its successors, which is 13 and 7, right? So it is more direct view. Just, it's kind of like closer to it, right? And then you calculate the EF and the LS. They are all calculated, right, with simple like a plus or minus with the duration, right? Yes. Okay, still downloading. Fine, it's fine. I'm gonna leave. Yeah, I was planning on let you do this exercises, this exercise in class, but since we don't have enough time, I think you can bring it back home and do it and submit it. All right. Okay.
But this is our homework for next year.
Yeah, it's gonna be a homework.
This is something else I think.
Well, this is gonna be, well, it's not the official homework. It's assignment in class exercise. But now since we don't have enough time, but let's do it, and maybe you can bring me a copy next time when we meet, so that we can discuss if that's right or wrong.
So it's separate with our actual homework.
Yeah, it's separate. Yeah. Okay. All right. So that's it for today. Thank you.